First of all, thank you very much to the organizers for organizing this conference. Thank you very much for inviting me to this conference. And I want to use the first minutes to advertise one of the papers of Jan, which I believe probably nobody knows in this. If somebody knows, just raise your hand. Okay. It's not what I expected. So we first met with Jan in 1987 in the place where I lived in Moscow, because Jan came to Moscow, and we became very good friends and talk about mathematics whenever we meet after that for long times, because it was great to talk to Jan. You somehow get his view on mathematics, on arithmetic. It was a great experience. But I also wanted to say how we met. So the reason for the meeting, as turns out to be, was this paper. And the meeting in 87, so the paper is, there's 12-year gap between this, was set by Boris Fagin, who came in January 87 to Prague for a conference, and then saw young Czech-Slovak mathematicians, and he came back, and he was quite excited. He said, you know, it's really great in Prague. There's lots of great young mathematicians, but there's one of them who is kind of shining, is kind of jewel among all of them, and they kind of worship him. His name is Jan Nekovář. And then he said that Jan talked to him about what he was doing, thinking about this time. This was a generalization of Weyl representation, metaplectic representation. It's a joke, of course, but let me emphasize this. So Fagin said that you should come to Moscow, and I actually worked before on this generalization of Weyl representation. By definition, it's a minimal representation of a Lie group. And so Jan came, we talked basically about this paper. And at that time, I wouldn't say paper was finished, but it was already clear what he's thinking about and what is going on. But it took him 12 years to publish this paper. And I think many people still don't know what happened in this paper. So his dream was to consider metaplectic representation of a GLN over a Deligne group and find kind of more structure there. Because even in the classical Weyl representations, there's more operators acting there. He never succeeded doing just that, but he did a Lie algebra analog of that. So he produced some extension of SLN by some nilpotent group for every n. And then he produced some representation of this group, so let's call it H of n SLN. And when n equals 2, he got just Weyl representation. When n equals 3, he got minimal representation of the group G2 out of his construction. And accidentally, before Jan, it has been done. And this was constructed by Sergei Gelfand in 1981. And the reason it was constructed is that this was the last project of BGG, Bernstein, Gelfand. And so they started doing something, and then Bernstein decided to immigrate. The collaboration ended, and they get up to this point, and now it's impossible to figure out what actually was the goal. But I believe their goal was somehow close to what Young did. And so I highly recommend this paper, because I believe that it's kind of, there is no references in math reviews to this paper. And I think it's a great paper, and I advertise as much as I can. Okay, yes?
What can I offer? Because I'm very glad you mentioned it. I wanted to mention it in my talk for exactly this reason. So I was a student of Jan, and when I started my PhD, he told me, oh, so if you want to read a couple of papers of mine, you can read this one and this one. And then he stopped and he said, and if you want to do something nice, read this one, because nobody has.
Yes. I believe, unfortunately, it's correct. And as I said, this was the subject of our many discussions in 87 and talking about these minimal representations. And I believe the potential of this paper is very far from being understood. So it's kind of worth somebody young to start looking at this. Okay. So my talk, I'm going to talk about explicit constructions of motivic Galois group, so to speak. It's going to be very, very elementary lecture, very, very elementary constructions. But I want to start with a general setup. And this is the only kind of abstract nonsense which you're going to see in the lecture. So, but I still let me say this. So let's suppose that we have the following data, abstract data. Actually, before I go into this, let me start with an example. So the main example I want to consider is before that. I want to consider several categories, and one of them is a category of mixed Q mixed Tate mixed Hodge-Tate structures. Q means that the weight filtration is over Q. And I want to describe the Galois group of this category. Now, in general setup, you have something like M, an abelian tensor category. And in this example, this is the category H. Then it comes with a subcategory P. In our setup, this will just direct sum of Tate motifs, Hodge-Tate structures. And it's semi-simple. And also tensor category. And the most important thing of this data is that for every object in the big category, there exists a filtration. So it carries some filtration, weight filtration. And it has a property that if you consider a functor assignment associated gradient for this filtration, which takes from M u to P, then the assignment is that this is exact tensor functor. And that's what happens in that example. That's all I want to say. There are some little technical fuzzy details. Let me skip them. So that's
Hodge-Tate.
So first of all, we're talking about the category of mixed Hodge structures.
Okay.
These mixed Hodge structures are Q mixed Hodge structures. This means that the weight filtration is defined over Q. Then when you tensor this over C, you get Hodge filtration. And then the condition Hodge-Tate means that HPQ equal to 0 if P is not equal to Q.
Okay, this is very simple.
This is simplest mixed category which contains Tate object. And so in this situation, we can define what I'm talking about, what is this motivic Galois groups or whatever. So I consider the algebra LM, which is derivations of this omega and derivations with respect to tensor structure. And this, by definition, means that it consists of all endomorphisms of this functor, such that if you evaluate it on omega of M1 tensor M2, then this is omega of M1 times identity on omega of F2, M2, plus identity on omega of M1 times phi on omega of M2. So you consider all these endomorphisms, and you get something. So this something is a Lie algebra, but not in the usual category of vector spaces, but in the category P, in the tensor category P. So that's the object which I wanted to consider in the lecture in different situations. And what I really want to study is the universal enveloping of this algebra being dualized. Oh, I didn't. Sorry, I didn't realize that. I know that's a fact. Thank you. It's okay, yeah? Almost okay. What? Anyway, so this is what I'm going to call the Hopf algebra of this category. So this is a commutative Hopf algebra in tensor category P. So that's the main object to study. Some commutative. This is so. You start with Lie algebra. You can take universal enveloping algebra of a Lie algebra. You can then take a dual for this object. Then, if you usually dualize your universal enveloping of a Lie algebra, you get a commutative Hopf algebra because this was a co-commutative.
No, but because of infinite dimensionality,
this is continuous dual. So you take. I have to explain how I'm doing this, and I have to assume that some kind of either say continuous or things are finite. But in the situation which I consider, this will be never a problem. Okay, so it's correct. So it's a even if you work with vector spaces, you're either talking about profinite Q vector spaces or in vector spaces. Let me not try to talk about this. You will see an example of what's going on. Okay.
Is it nilpotently algebra, kind of topic?
Yes. This is nilpotently algebra in a semi-simple tensor category. This means that if you would have a further realization functor to vector spaces, you will get semi-direct image of the Galois group of that category P and some nilpotently algebra. So that's the Galois group I'm talking about. Okay? Offer?
Yes.
Okay. So that's the end of the abstract nonsense part. And so the key point which I want to kind of emphasize in this lecture is that often HM has a canonical explicit construction. Which is behind all explicit constructions of regulators and things like that. So now let me do this in the case I'm talking about, this category HT. So in this case,
Please define LM as phi in end omega.
So LM is a you have a functor omega to the category P, and you can consider endomorphism of this functor. That already will give you this U.
But this is just as a vector. This is as a vector space.
There is no vector spaces here. We're talking about semi-simple tensor category P.
Okay. So you want to define it as a P object.
Yes.
By saying that okay, that it's points with values in some object of phi is something.
I'm just saying that I can proceed formally. I have fiber functor in semi-simple tensor category, so I can get out to L out of this. Okay. So in this, again, in the situation which I will consider in a second, we essentially will be working with the vector spaces. So it's okay. Now, the most important thing is that we have objects in this category, Q of 0 and Q of n, and we know what X groups are between these objects. And they are C divided by 2 pi I to n q. This is when n is this is when this n is bigger than 0. And we also have x0 between q of 0 and q of 0. And this is just q. And everything else is 0. And because we get a category where between the generated objects we have x1 given to us explicitly and x2 and higher equal to 0, this immediately implies that this Lie algebra we are talking about is free. And more precisely, it implies that if you want to talk about this commutative Hopf algebra, which is a dual of universal enveloping of Z, and then this is just a tensor algebra of the direct sum of the first x C divided by 2 pi I nq, where n goes from 1 to infinity. I will remind you how you make this as a Hopf algebra. In a second. But I want to say immediately that this description is absolutely non-canonical because, like free Lie algebra has huge amount of aftermorphisms, and for many reasons this is certainly non-canonical isomorphism. Another one I'll give you in a minute. Now, what is this Hopf algebra? So that's a general setup again, that if you have a vector space, let's see if it doesn't matter, finite dimensional. Then, if you consider tensor algebra over this vector space, this is always a commutative Hopf algebra. But how it becomes commutative Hopf algebra? What the construction? So it has product, and the product is commutative. It's given by the shuffles. It's shuffle product, and the simplest example is that product of two elements is tensor product of one in one order plus tensor product in the other order. And for more complicated tensors, it's shuffle product. And has a coproduct. So the coproduct is given by deconcatenation. And we denote this by delta. This is sum of its components. And a given component it takes tensor with p plus q factors and maps it to the tensor which you get by cutting this tensor product of p plus q terms somewhere in the middle, the place p. So this goes to v1 tensor and so on tensor vp tensor vp plus 1 and so on tensor vp plus q. And the statement is that this T of V, as well known, it's a commutative Hopf algebra. Okay. Now, why this isomorphism is non-canonical? Yes.
Is it tensor in the middle?
What?
Yeah. Is there a tensor in the middle? Yeah.
Sorry, what?
Yeah.
Sorry, I don't hear, Matt.
What's written just looks like the identity tensor.
No, it's not objective.
There's the T tensor T.
It's so if you have since even so it's a map from T of V to T of V tensor T of V, and this is one element of T of V. This is another element of T of V. Okay, thank you. So now why it's not canonical? It deserves to be explained in several ways, and here is one more. So here is an observation which plays a crucial role in the story. So if you take any triple given by object of your category, mix Hodge-Tate structure, and some vector and covector, and to be precise, this F is going to be a linear map on GR W minus 2n of your H to Q of n. And this V is going to be a map in the dual direction from Q of 0 to GR W0 of H. So if you have this data, object, and covector and vector, then it immediately produces you some invariant, which lives in this Hopf algebra. So let me call it like P of this H, V, and F. And it lives in this Hopf algebra we are talking about, in our case, as Hodge-Tate structures over Q. Okay? And actually, in this case, this Hopf algebra is graded, and it actually lives in this degree, part of the degree n. But we always have such a map. Now let's see what happens when n equals 2. So if n equals 2, so when n equals 1, this Hopf algebra So it gives you some abelian group, some vector space. And this is just C star, because that's the x1 q of 0, q of 1, n equals 1, ht1. But h2 is a little more complicated. It's supposed to be c divided by 2 pi I square q plus c star, tensor c star. This is because we're talking about tensor algebra, which is generated by this vector space. And this nth term in this vector space has degree n. And therefore, if you want to get something of degree 2, you either take something which already has degree 2, or take tensor product of two things which have degree 1 and 1. And this is the first x, and this is the second x. So we're supposed to have, we do have such a decomposition, but there is no way we can get this element naturally living here. It's supposed to live here, of course, but not naturally, because if it's direct sum, you can further project it to this part. And then you can convince yourself by any means that this is not possible, because if you take any variation of Hodge structures, for example, the one which corresponds to the di-logarithm, it's a multivalued function, very much multivalued function. And there is no way you can naturally produce invariant of this function with values in this abelian group. Just such construction does not exist. And you can go to higher, like n logarithm doesn't have this invariant. So we never ever, when we talk about multivalued periods of variation of Hodge-Tate structures or multivalued functions of this origin, we can construct the real valued versions like Bloch-Wigner function, but we never ever can construct the complex valued function by any means. That's not possible. But on the other hand, we do have this invariant. And so my whole point is that we should do better. We should describe this Hopf algebra explicitly, and then we are going to get this invariant, but it will be sitting in a more complicated space. Very explicit, but more complicated. So let me do this. Actually,
the first thing is C star modulo torsion.
Oh, no, modulo torsion, yeah.
What?
Not all C star.
Oh, I forgot to say. Sorry. You're right. I want to mention, especially seeing offer in this room, that whenever I write this, I always mean all abelian groups are Q vector spaces. I always kill torsion, and I don't want to write this down. OK. So sorry about this.
Can you just remind us what is invariant P H?
What? Oh! No, thank you. I just forgot about this. It's in my notes. I forgot to do this. Sorry. This is actually important. OK. What is...
Said that this invariant lies in this script H, this kind of
commutative Hopf algebra.
In this commutative Hopf algebra. You also said you can compute it.
Yes.
And then you said that in some particular cases, like the multi-D logarithm and so on, you cannot get, I don't know.
Yeah, exactly. So let me make your question explicit once again. So Offer said that I said that you have this invariant. Yes, I have it. And I have it with values in this vector space, so to speak. And then this vector space is isomorphic, but in non-canonically. It's isomorphic to direct sum of two vector spaces.
But this is, it is non-canonical. Okay.
Not that I know, I'm saying that if it would be canonical, I will get something which never exists. Like I would get a complex period of, let's say, di-logarithm, which does not exist even if you mod out it by 2 pi s squared q. Because dialog has more complicated monodromy than just 2 pi s squared q. So it's not possible. Tony's question. So the definition is the following, that if you have this endomorphism, then what you can do, you can take this endomorphism, apply this to the vector which I have, and evaluate my covector on this vector. And so by this construction, this is a matrix coefficient. And so roughly speaking, it's a map of linear vector spaces in this case. And so this gives you element of the dual of this endomorphism of omega dual. But that's exactly by definition my U of HT. Okay? All right. Now comes the main point. I want to give a construction. And the construction is very, very simple.
Again, I'm not sure about this and U, because when you say is it the same and as before and omega? What before when you had and omega? Is it a vector space over the field?
In this particular case, we are talking about Hodge-Tate structures. Yes. I can basically say this is a vector Q vector space. In order to say this, I take associate graded, and then for each part which has degree n, just take home from Q of n to this object, so I get a vector space. It's basically multiplicity of the Q of n which you get associate graded.
Okay, but this is and in a categorical sense inside the category
P. But in this category P is just the category of graded Q vector spaces.
Okay, so I'm okay, so it's always the internal and in the okay.
So
the star.
It's a dual. Sorry. Now comes the main point. So I introduce some commutative Hopf algebra. Called A of C. And I wrote, and I say again, that this is joint work with my former gradient student, Guangyu Zhu. And it's in the archive. So the definition is the following, that this algebra is a graded algebra. Is direct sum when n equals 0 infinity of the graded components. And the simplest of them is just Q. But the others are defined as follows. So as I said, this is the main point. That this AN, by definition, is C star. C star means C star modular torsion. So it's C divided by 2 pi square Q. Tensor over Q. C, tensor and so on, tensor C. And there are exactly n minus 1 terms in this product. So the first of them is C star, but the others getting then the products of C as many times as needed. Now, then the question is, what is a coproduct? That's very easy. Again, I write this as a sum of components. And the coproduct is basically given by the same formula, but let me write it down again. So I have C star, tensor C, tensor and so on, tensor C, tensor C, tensor and so on, tensor C, and I have Q summands here, Q factors here, and P minus 1 factor here. So I have altogether Q factors here. That's where it starts. So it originates from a P plus Q. And it goes by this delta PQ to AP tensor AQ. And how can you go from there to there? So it's very easy. You just cut here. But you're not yet there. You're supposed to project to C star. So that's the coproduct. OK?
So by exponential.
Yes, yes, yes. So more formally. Yes. OK, I think it's clear what it is, but I can write you form. So you cut it into pieces in a natural way, and then here stands complex number. You take exponent of this complex number, so that 2 pi I is killed. So get to C star. OK? So what really stands here is C divided by 2 pi I.
So it's all based on rational vector space and one-dimensional subspace, yeah?
Exactly, yes. So the whole story, as Maxim said, the whole story is invariant actually of the pair, which is, let me write again. It's a pair which is given you by just 2 pi I Z, you can say Q. Maybe I should say Q, but and complex numbers. So the coproduct is very easy. What is a product? The product is more interesting, and somehow that was the whole point. What is the product? And what is this group? So So to define the product, let me start with some example. Let me multiply two things. So let me the simplest so this is the main point I'm saying. Simplest instance is a map from symmetric square of the vector space C star to vector space C star tensor C over Q. How you do this? Huh? Sim, oh yes, Sim2. Thank you. So you take A tensor B, two elements of the multiplicative group complex numbers, and you want to map them to A tensor log B plus B tensor log A, because that's exactly what would mimic this formula. So it's a shuffle product. The only caveat is that this is not defined, because this is a multivalued function, this is a multivalued function. It does make sense. And so we add correction term minus exponent of log A times log B divided by 2 pi I and multiply by 2 pi I. Now you can easily see that if you vary log A, for example, what? Huh? So if log A goes to log A plus 2 pi I, two things happen. So first of all, here we'll have additional B tensor 2 pi I. But here you will get, instead of this, you'll get extra 2 pi I. So it will be cancelled, and you get exponent of log B tensor 2 pi I. It will be cancelled with a minus sign. So it's OK. It's well defined. OK, now let's generalize this. So first of all, I want to define some kind of product called M from the tensor power of C, not from my A, but tensor power of C to tensor power of C to itself. And then I will project it where it's supposed to lie. And so I do this by picture. So I imagine that I have tensor product of several elements, like OK. Let me call them. So I want to define M prime of x1 tensor x2 tensor x3, comma. And I want to put here like y1 tensor and so on, tensor y5. So how to define this? So this I picture as 3 points, different points on a line. So it's x1, x2, x3. And the others I picture as a 5 points on the line. And these 5 points are those. It's y1, y2, y3, y4, y5. And now what I'm going to do, I'm going to shuffle red with white. But the usual shuffle is a procedure where you take, where you kind of move this through that and you never collide. Now I'm going to collide. And so the typical term will be the following one. There will be something like that. So first of all, I still have my points x1, x2, and x3. And they're different. I mean, they may be coincide, it doesn't matter, but let's assume they're all different. But then we have y's, and y's can be anywhere. So for example, you can have here y1, but you can also have here y2. You can have here y3. You can have here y4, and you can have here y5.
So y2 can be in the same place as x1?
So this means that these 2 points, y2 equals x1, and y3 equals x2. It's an example. They collided. They may all go through. Then I have something just a tensor product of them. the simplest situation. Okay? Offer. Okay, let me. So look, let's suppose you want to take this point x and collide this with this point y. Then three things can happen. You can either have one goes through the other, so you can have this, this, or you can have them collided. Okay? Then this gives you x tensor y, this gives you y tensor x, and this gives you minus xy divided by 2 pi I tensor 2 pi I. That's the procedure I'm talking about. And after that, I will put it where it's supposed to live, because the first term always supposed to live in C star, so I will exponentiate the first term. Okay? So for example, what stands here is the following term. So we have y1 tensor y2 x1 divided by 2 pi I, tensor 2 pi I, tensor y3 x2 divided by 2 pi I, tensor 2 pi I, tensor y4, tensor y5. So I have correct number of terms. Supposed to be 8. 1, 2, 3. Oh, x3. I missed x3. So
It collides after that you put extra 2 pi I, yeah?
So yes, exactly. The rule is that if two points collide, I do the following. First of all, I divide by 2 pi I. And secondly, I multiply by 2 pi in the next factor. This way, what is I doesn't matter. You can take minus I, the result will be the same. And actually, you can multiply by lambda 2 pi I, it will be the same. So only line important, not the generator. Secondly, in this case, the sign will be plus. So, and in that case, it was minus. This means that the sign is how many collisions you had. Okay, so this defines you some product, then you project to this C star, tensor C, tensor and so on, tensor C. And I claim that we are done, that this is a Hopf algebra, and that's exactly what we want. So, theorem.
So of course you have to take logarithms before, because some of the terms involved in C star, so you take arbitrary logs, do this and say it's independent because you will somehow do the...
I cannot make even slightest mistake in your presence, or even kind of omit something. Yes, absolutely. If I really want to multiply C star tensor CCC, tensor C star tensor CCC, so I do the following thing. So let me write it here. So you want to multiply a P of C, you want to multiply this to a Q of C. And you want to end up in a P plus Q of C. But you start from the lifting of any element you have here to just tensor power of C. Just P's tensor power of C. So there is a projection, canonical, exponent times identity, and you take any section you like. And then you have here tensor Q of C. You multiply them by the product which I just defined with all these collisions. You land in tensor P plus Q of C, and then you project down, taking exponential respect to the first term. Okay? So theorem is that we got a Hopf algebra, commutative Hopf algebra. This guy A dot C is a commutative Hopf graded in a natural way by n Hopf algebra over Q. And there exists a canonical isomorphism is what we need. So and see that in this case canonical isomorphism of commutative Hopf algebras, which takes you from let's say, this H from the category of Hodge-Tate structures to A dot of C. So this isomorphism is canonical. Now, why it's useful that is canonical? So before I explain why this is useful, I'm going to give you an example.
It means that it's based on any commutative algebra over U and any invertible element.
Not any, but one-dimensional invertible element, yeah. Basically any, yes. Yeah, any, yeah. Yes. And I believe I will not have time to go through this. Then the same story goes in 3 different situations, and it will become different every other time, especially over periodic numbers. But you're absolutely right. So why this is good? I want to explain how I construct this map, this big period. And I prepared an example. It's a somewhat elaborated example. So I want to construct this kind of big period called list 3 of a number z. And so it's supposed to land in C star, tensor C. And it's given by the following formula. So the main term is exponent of minus the usual trilogarithm of z divided by 2 pi I squared. Tensor 2 pi I, tensor 2 pi I. Then you have plus exponent of logarithm square z divided by 2 pi I, tensor 2 pi I, tensor log of 1 minus z. Then you can have z, which is exponent of log z, tensor minus Li2 of z divided by 2 pi I, tensor 2 pi I. And then you can have minus z, tensor log z, tensor log 1 minus z. So the formula look kind of complicated, but I will first of all will explain how you get this formula. And secondly, if you don't know how you get it, then the kind of the miraculous fact, which is explained by construction, but a priori, the main fact that this expression is well defined. Well defined in the sense that if you analytically continue all functions over the same path, then if you do it over different paths, you'll get exactly the same elements, that the monodromy will cancel out. Just like the example which we have is multiplication, but more complicated. Now, how you do this? And now I will just construct this map.
So, what does it mean in terms of your theory of? So, does it correspond to some mixed Hodge?
Yes. When I say take a trilogarithm, I was about to write this. When I say a trilogarithm, so we know that trilogarithm means a variation of Hodge-Tate structures. And actually it means a variation of very specific Hodge-Tate. I mean, it's some concrete variation which I'm going to write. So it's a matrix, period matrix 1 minus Li1 of z minus Li2 of z minus Li3 of z. Then you have here 2 pi I. Then you have a 2 pi I log z, 2 pi I squared. Then you have 2 pi I squared log square z over 2 pi I, yes, right, log z, and then you have 2 pi I cube. So you have this lower triangle matrix. And then what I'm doing with this matrix, so imagine you have such a matrix. Then I think about this in the following terms. So I'm just drawing a cartoon for this matrix. And then I'm taking all possible products of periods. I can take this multiplied by this. Or I can take a similar thing. I can just take one big period. Or I can take.
What does this matrix represent? You have some.
So this matrix is a collection of multivalued functions which are defined by simultaneous analytic continuation of log 1 minus z, the log of z, and trilog of z. I can explain how. Now, when you draw this matrix, this means that this is matrix of periods. This means that you can get a Q vector space, and you can get a Hodge filtration and weight filtration in this Q vector space. And so the columns of this matrix, the Q linear combinations give you the Q vector space. And so the main statement that if you take monodromy, you get to one column rational multiple of the other column. And then there is a Hodge filtration in the opposite direction. That's the meaning of this matrix, but then I won't explain not this, but where do I get this formula? There's 4 terms, and basically they correspond to all ways I can draw staircase from top to the bottom. So for example, this staircase corresponds to main term, exponent of Lie 3, because I'm talking here about period, this kind of period. So the one which you have the next one corresponds to the third term. So this is term number 3, this is term number 1. And there are, you can keep going, but I think that the pattern is clear from here. And you also understand that you can do this for any variation of Hodge-Tate structure. It's exactly the same procedure. The important thing, so you multiply by some powers or divide 2 pi I, but otherwise you're just talking about taking all possible periods and multiplying them in this tensor product. Now, what's good about this? So let's suppose you want to construct a regulator. So as an example, let me talk about regulator from K5 of Q star to C divided by 2 pi I cube Q. This is what's called Beilinson regulator. So the Borel's regulator goes to real numbers, but this goes to basically C star. Now, how you construct this regulator? It's known that you have to write down something like sum of trilogarithms of certain complex numbers Zi, and then they satisfy certain algebraic condition, something like 1 minus Z I tensor Zi tensor Zi equal to 0 in some tensor product of 3 C star, something like that. Not trying to write down condition. That's an algebraic condition. But then if you have any collection of numbers Zi, you can try to consider this function, this number, but this number makes no sense whatsoever because it's a multivalued function. You cannot speak about its values. However, if you think that you're taking here this big period, which is well defined, then this lands in C star, tensor C star, C, tensor C, and there's a map from here. Okay, let me do it a little better. I'm doing the same, but I'm just putting more detail. So you have the following complex. C divided by 2 pi I cube Q going to C star tensor C going to C star tensor C going to C star tensor C, and the last one will go C star to tensor product of 3 of them. So you have this complex, and this complex is exact. It's very easy to see. Now, the sum which I consider is sum of this Lie 3 of the i's, which lives here. But assuming the algebraic condition, which I kind of mentioned but didn't formulate, I'm assuming some algebraic condition. It will have a property that this map, let me call this map delta, will annihilate this. And this just means saying that the sum lands where it's supposed to land, in C divided by 2 pi I cube Q. So this is the regulator. And so the bottom line is that you construct a regulator based on the level of complexes, and the complex to which you map is this cobar complex of the Hopf algebra which I defined. And then the condition that's a cycle of complex will guarantee that you land where you land. But in any case, this expression is always well defined. There's no questions about multivalued nature and so on. Now, I make example when n equals 3, when n equals 2, the element Lie 2 of Z, it's a Bloch's element. from 1978 paper. Okay, huh? But other than, the others are new.
So the Bellinson regulator is the one which was defined using Deligne cohomology, or?
Both Bellinson, you have, in the case of number fields, you have Borel regulator and you have Bellinson regulator. Bellinson regulator is kind of finer because it takes value basically in C divided by 2 pi I NQ. It's defined in terms of Deligne cohomology. So the question is, where is Deligne cohomology? I'm going to answer this in a second.
It is not defined on K5 of C. It's defined only on K5 of...
I just don't want to go into details, talk about associate graded of K5, talk about Adams filtration. I just try to keep it simple, okay? It doesn't matter. It is defined exactly where you said. Okay, now the next thing I want to do, I wanted to say that this construction, I have like 7 minutes left. Okay. This construction can be applied in some other situations, and it will deliver you also something which relevant to regulators in all cases. So here is the next one. Let's consider category HT related to complex variety X. And then there is a category of variations of Hodge-Tate structures on X. And then there is a derived version of this. And I'm going to construct the corresponding Galois groups. So it is done just like Maxim noticed. You have just two guys here, 2 pi Q and C. In this case, you just start with the de Rham complex of X and the same 2 pi I Q. And so I claim that if you apply the same exactly construction here, then you'll get some commutative Hopf differential graded algebra. So let's call this guy a dot of omega dot x. Now, how you define this guy? It's graded as before. You're right. So I bet I can talk about sheaves, but
Or if it's a fine variety, consider.
or you can assume it's a fine variety. The construction, let's assume it's a fine variety. So what I do, I'm saying I have a n of this omega x, and it's exactly the same thing when n is bigger or equal than 1. So I take the de Rham complex divided by 2 pi iq, and then I tensor it with many products of the de Rham complexes. So here I have n minus 1 factors. And by exactly the same construction as before, this is a commutative Hopf algebra, because it has coproduct by deconcatenation and product by this construction. But it also has a differential. And how the differential works, so if you want to calculate d of element x1 bar, this projection to C star x2, tensor so on, tensor xn, then what you do, you take differential in the de Rham complex of this x1 and multiply by x2, then tensor the rest. Then the next term will be plus minus x1 bar tensor differential of x2 multiplied by x3 tensor x4 and so on. So you just use this kind of product dxx every way and take plus and minuses in a natural way. So I claim this is differential, and that's what makes out of this guy commutative graded Hopf differential algebra, differential Hopf algebra. Now, what is the meaning of this algebra? So it provides you the Deligne cohomology in the following way. The theorem B so theorem is, let's say it was A, theorem B. If you take cobar complex, and I will remind you what cobar complex of a Hopf dg-algebra in a second, but if you take cobar complex of this Hopf algebra, and it has additional grading by the weight, and you take the n grading n part of this cobar complex, so you get this complex, and the claim is that this complex is canonically quasi-isomorphic to Deligne complex. It's a Q Deligne shifted by n, twisted by n x times. But what happens here is that indeed for every n you get a complex which is quasi-isomorphic to Deligne complex, but which is bigger. But however, the point is that this guy is a Hopf dg. And so what you get such a presentation. So if you consider direct sum of all cobar complexes, this is, you get something, and this something reproduces the direct sum of all Deligne cohomology. So the bottom line is that you now have a differential graded version of direct sum of all Deligne cohomology, and this Hopf algebra is somehow the Galois group of the corresponding category. So again, the point is that, let me remind you that when Bellinson originally defined what's called Bellinson-Deligne cohomology, he defines the product, and this was a kind of new and subtle thing which is needed, the main ingredient of construction of the regulator for him. And this product was subtle because it was neither commutative nor associative, but it was commutative up to the homotopy and associative up to the homotopy.
On what? On the Deligne?
On Deligne, we have Deligne complexes, the standard Deligne complexes. Yeah, okay. And up to omega n minus 1. And then Bellinson defined some product. And then this product is neither commutative nor associative, but it's in derived category it is commutative and associative, but it's not on the nose commutative and associative. This one is commutative associative on the nose. So the model is bigger, but it's the DGA model for that. So, or other way I would say that we talked about category of variation of Hodge structures, and we should have not only derived category but the DG category, and this is this DG category is the category of DG comodules over this Hopf algebra. Or you can do other things. You can take H0 with respect to this differential of this A of omega, and then if you consider this comodules, then this is canonically the category of variations of Hodge-Tate structures on X. And the fact that you take here cycles with respect to D, this is somehow equivalent to Griffith's transversality condition. It explains you why you have the shape like dx.
So discrete D, then lower the degree by 1?
What?
The differentials lower the degree by 1?
Differential, I think it is.
There are several degrees here. But
No. Let's talk. So there are 2 degrees here. So the one I'm talking about at this moment, I'm talking about the weight degree. And then there is a degree which comes from the de Rham complex. There is a cohomological degree, and I didn't even mention this. Okay? But then there is a weight degree, which I use in that formula. And the weight of x1 tensor and so on tensor xn, by definition, is the sum of the cohomological degrees plus n. And so this is the weight degree I'm talking about here. And the cohomological degree, it behaves as it should. It's a different. I said weight. Yes. What?
You say cohomological degrees.
I said not what I want to say. It's a weight degree everywhere. Okay.
The differential preserves the weight.
Yes.
This differential here is that's the same as the one.
No. This differential here is somewhat different. So I have to introduce differential on the cobar complex, and I didn't do this. I didn't even introduce the cobar complex. So maybe we.
Okay, this is another thing.
This complex has this differential, but it's also a cobar complex. So, okay. So my time is out, and I just wanted to say just 2 30-second comments that you can do. First of all, this is the crystalline setup. And you can do the same in the semi-stable setup. And the construction is exactly the same. Namely, the key thing here is that you have the fundamental, you have T, which is 2 pi I of Fontaine. And then you have this B crease. We are on p-adic side, and I'm going very, very quickly, so I don't have time to. So this is the analog of my Z of 1, C star. And so now I treat it as I'm supposed to treat this analog. So this means that I produce AN crease, which is by definition just this, you can say it's B crease phi equal 1 divided by T, tensor B crease, tensor and so on, tensor B crease. And this gives you Hopf algebra, commutative Hopf algebra. And this is the one which is responsible actually not the category of crystalline representations, but the category of this BKF Bruel. I mean, I have no time to talk about this. This was category of rigidified BKF models, and I need to consider the only part of this category consistent of objects with weight filtration. Then the Hopf algebra I get here classifies that category. And the second example, I'm finishing. So the second example is that I can take B semi-stable, and in this case, I treat it as a de Rham complex. So if you know what I'm doing, then you know what I'm doing. So maybe I don't want to say this. So you have ring B crease, but you also have ring B semi-stable, and so you can introduce this Hopf algebra, and it's defined the same way as before. So the main thing is that you introduce some complex and gives you differential, and then you take this complex, let's call it R semi-stable. You take this complex divided by T, tensor this complex, and so on. And you get again Hopf algebra, and this Hopf algebra is responsible now for semi-stable representations. So that's it.
Do you get theorem B then for symptomic cohomology?
I think no. I mean, we didn't claim this. So I was supposed to say that there is a work of Jan Nekovar and Vishen Niziel, and work of Vishen Niziel and some other works, where the subject actually of all these regulators, p-adic regulators, atomic regulators, was tremendously developed. This is one of the reasons I'm talking about this here. But I don't go that far away. I'm just saying that I produce Hopf algebra, and it's supposed to. I mean, we don't prove theorems about analogs of Deligne complexes here. It should be true, but we.
I have a very difficult question.
Yeah.
Is this on the archive?
Yes.
Okay.
It's a very nice question. So you have, seems that you have the same construction in various settings.
Yeah.
So can you axiomize? You start with your length 1 complex, and you start with the complex of length 1, right?
Yes.
And then you construct a commutative Hopf algebra. So what would be the minimum axioms to construct that?
I can formulate these minimum axioms, but in fact, if you go to the Deligne homology, it's already it involves already big complex, de Rham complex. So in the paper there is an axiomatic definition, and basically this definition says that all you need to have some differential graded algebra. But then in the p-adic case, there is also action of the Frobenius, and you have to take Frobenius equals to p. Maybe I made some mistake when I was writing here. Hope not. Anyway, did I say this mistake here? You have to take when Frobenius equals to p part, and this is not a subalgebra, but this is a space which is the analog of C, and this is the analog of the de Rham complex. So that
you said that the base on associativity and commutativity up to something higher.
He had up to homotopy.
In the language of today, can we make this more precise?
But that's exactly what we did here. So
it's an incarnation maybe of this.
No, we produce differential graded algebra which produce you all Deligne complexes, and they form differential graded algebra, so the product on these complexes is commutative and associative on the nodes just by construction. The claim is that this algebra is actually comes from it delivers Deligne cohomology. I can explain this, but yes, so we produce DG version of the derived category of variations or whatever, and the Belinson's complexes is what is a complex which calculate X groups there. But he didn't have construction which is commutative associative on the nodes, so this is a construction which is commutative associative on the nodes, yes.
In particular, it is commutative and associative after all aeromotor is in the...
No, here it's on the nodes, it's a DG world.
But in Bennington it was up to...
Yes. And this work actually was the most amazing part, because we haven't, I mean, my generation haven't seen before somebody working easily in derived categories and just producing something up to homotopy and so on. So far, this was the first example. It was very remarkable, but you can get out of this.
And there's a non-Tate case.
Huh?
Non-Tate case.
There is a continuation of the story. I can talk about, I mean, I cannot talk about this, but you can consider different setups. For example, you can consider setup not Q Hodge structures, but real Hodge structures. And then you talk about category of variations of real Hodge structures. And then there is a similar story, but it's actually even better, because you get not only construction of the corresponding Galois group of a point, it comes with canonical generators. But it's a kind of canonical construction as well. And it works in families in the right version, so on and so far. So this is with real coefficients. I don't know what periodic numbers should exist, but it's not my...
Just a question on theorem B. Do you assume X projective?
No, I don't assume anything about X.
You don't need log poles?
No, of course, if X is affine and not projective, then you have to consider the RAM complex with logarithmic singularities. Absolutely. Yes.
Any other question? Then we thank Sasha again.